Myself, Sundaram, Professor, Sri Ramakrishna Engineering College. This video is about Thevenin's and Norton's theorem. This video covers impedance and admittance of AC circuits, voltage and current division in AC circuits, source transformation, Thevenin's and Norton's theorem. First, let us see about impedance, admittance, current and voltage division in AC circuits. Let us see this example. For the circuit shown in figure, find A. The total impedance, B. Total admittance, C. Current I in the circuit, D. Voltage V1, that is voltage across resistance R1, E. Current flowing through the capacitance C, and resistance R2. So this is the given circuit. So L is 2 henries, R is 1 ohms, and across this voltage is marked as V1, and this is the polarity, and C is the capacitance 0.1 microfarad. R2 value is 4 ohms, and the voltage source is 10 cos omega t. This in polar form it can be written as 10 at an angle 0 degree. So 10 cos omega t is voltage in time domain. So when you write in polar form, you should write it as 10 at an angle 0 degree. So normally we used to write 10 cos of 2t plus theta. So in this case theta is 0, so therefore we are writing here as 0 degree. And this is the current you are asked to find out. The first step is, so from the given voltage, so we know the magnitude and phase angle of this voltage, and the omega, in the place of omega we have 2 radians per second. Then find out the inductive reactance. Suppose only if the inductance and capacitance value are given, we have to find the reactance. So inductive reactance is j omega L. So omega is 2, and you get this value as j4 ohms. Capacitive reactance, it is 0.1 farad is the capacitance value. Substitute in this formula 1 by j omega c. Omega is 2 radians per second. So we'll get this value as minus j5 ohms. So now redraw the circuit. Now instead of inductance and capacitance value, write their reactance values. Now let Z1 equal to 1 plus j4 ohms, that is this branch impedance, let this be 1 plus j4, and this branch impedance, let this be Z2 equal to minus j5, and let this be Z3 equal to 4 ohms. From this diagram you can say that these two are parallel, and this equivalent impedance comes in series with this. So the formulas are similar to the formulas that you have used for resistive network, and instead of resistance here we are using impedance. So ZAB, so ZAB is Z1 plus Z2 in parallel with Z3. So if you see here, Z2 is in parallel with Z3, and this comes in series with Z1. So now you substitute the values 1 plus j4 plus Z2 is minus j5 and Z3 is 4 ohms. So Z2 in parallel with Z3 can be written as minus j5 into 4 divided by minus j5 plus 4. So this comes to be around 3.44 plus j2.05 ohms. Similarly, ZCD, that is impedance between these 2 points is, so that is this reactance and this resistance, they are in parallel. So the parallel combination gives the impedance across terminals ZCD. So Z2 in parallel with Z3, so that is you get 2.44 minus j 1.25 ohms. Now coming to the admittance. So admittance YAB, so this will be equal to 1 by ZAB. So inverse of this will be YAB. So how to get this value? So this will be equal to YAB equal to Y1 in parallel with Y2 plus Y3. YAB equal to Y1 parallel with Y2 plus Y3. So if the impedances are in parallel, their admittance you have to add, just opposite to that of the impedance. And suppose in impedance, if any two impedances are in series, we will add. But here we used to write admittance are in parallel. Y1 in parallel with Y2 plus Y3. So this gives 1 by 1 plus J4 is Y1. This parallel with Y2 is 1 by minus J5 and Y3 is 1 by 4. That is, if you want admittance of this, it is 1 by 1 plus J4. If you want admittance of this, it is 1 by minus J5. If you want admittance of it is 1 by 4. So now you find out this value and this value. Since you have to find the parallel combination of this, so multiply these two and write it in the numerator, and you add both and write in the denominator. So you will get this value as 0.214 minus J 0.128 Siemens. So it is denoted by letter S, or also its unit is mho. Then coming to the current I. So if you want to find current I, so you know the impedance across the terminals AB. So that is the impedance, total impedance comes across the source. So if you divide voltage B divided by the total impedance is at AB, you will get the current. So this comes to be 2.15 minus J 1.28 ampere. Then coming to the voltage V1. So here there are two ways to find out this. If you want to find out this voltage, already you know the current, multiply this current with the resistance, you will get this voltage. So that is I multiplied by 1 ohm. That will be 2.15 minus J 1.28 ohms. So in polar form, it is 2.5 at an angle minus 30.76 volts. Method 2, you know already ZCD, the equivalent impedance here. So this you know equivalent impedance, and here we have a inductance, and here we have resistance. So there will be three elements. So now you apply voltage division. Voltage division will be, if you want V1, the total voltage applied across the network multiply by R1 divided by sum of all the resistances and reactances in the circuit, that is J4 plus 1 plus ZCD. ZCD already we have found out. So ZCD is 2.44 minus 1.95 ohms. So now you substitute this formula 10 at an angle 0 degree into R1 by Z1 plus ZCD. So now you substitute all the values. R1 value is 1, so you'll get this value as 2.5 at an angle minus 30.76 degrees volts. It is same as that of the value we got for V1 in method 1. Coming to the current divisions, let us find current through the capacitors and resistance using current division. It's very simple. So you know the total current. So if you want to find current through the capacitance, use the current division formulas. That is the total current multiplied by the opposite branch resistance divided by sum of this resistance and this reactance. And similarly, if you want find out current through resistance R2, so the total current should be multiplied with opposite branch reactance. In this case, it is minus J5 divided by sum of these two, that is 4 minus J5. So IC is total current into Z3. So this is Z2 and this is Z3. So that is Z3 by Z2 plus Z3. So substitute the values. So this you will get it as 1.56 at an angle 20.57 ampere. Similarly, current through resistance R2. So here IR2 is I into the opposite branch impedance, that is Z2 divided by sum of the two impedances Z2 plus Z3. So this comes to be around 1.95 at an angle minus 69.42 degree ampere. Then coming to the next example, find Z for the circuit shown in figure from across the terminals A and B. So this is a circuit. You are asked to find the impedance across the terminals A and B. So you have to look into the terminals towards left. So if you see this circuit, you'll find that this XC1 is in parallel with R. So these two branches are in parallel. So this comes in series with this capacitive reactance. So here only ohms is given. You have to add minus J to the capacitive reactance. If it is inductance, you have to add plus J. So now Z will be equal to, so these two are in parallel. R is in parallel with XC1. So R into XC1 divided by R plus XC1. This is for this equivalent impedance. Plus this comes in series, that is plus XC2. So you substitute all the values. So here 100 at an angle minus 90. This is for minus J100. Minus J100. So for minus J, you have to add angle as minus 90. And similarly for 50, you have to write it as 50 at an angle minus 90 or minus J. So substitute the values. So you'll get this value as 24.8 minus J 128 ohms. Then coming to star delta and delta to star conversion. So sometimes in network protection, so we may have to use this star to delta conversion or delta to star conversion. So let us see the formulas. So this is the network. So this is a star network. The impedances are named as Z1, Z2, Z3. Delta connected network, it is ZA, ZB, Z6. So you have to know how to draw this. Suppose if you are going to draw this star connected network Z1, for example, this branch is Z1, Z2, Z3. So you name this node as A and this node as B, this is C. Now what you do is, while you name the impedance of the connected network, so the impedance exactly opposite to Z1 should be named as ZA. Then the impedance exactly opposite to Z2 in the delta connected network is named as ZB. Similarly for Z3, the opposite impedance is ZC. So you have to name like this. If you have named like this, then you can easily write the equations. We see all these equations, that is Z1 is the impedance of the star connected network, Z2 is the impedance of the star connected network, and also Z3 also impedance of the star connected. So here Z1, Z2 and Z3 are in terms of delta connected impedances. So here if you see in all the expressions, the denominator is common, ZA plus ZB plus ZC, whereas numerator only will vary. So we will see how to remember this. So Z1, take Z1, this is connected to node A. So node A, you find out what are the impedances that are connected to this point in the delta network, that is ZB and ZC. So in the numerator you write ZB into ZC divided by sum of all the impedance of the delta connected network. Similarly Z2, you go to Z2, this is a point. So ZC and ZA are connected, write it in the numerator. So ZA into ZC divided by ZA plus ZB plus ZC. Similarly Z3, so ZA into ZB divided by sum of all the impedances of delta connected network. Then coming to star to delta conversion. So here ZA, ZB, ZC, they are impedance of delta connected network. So we are going to write expressions in terms of impedance in star connected network. So let us see how to write this. So here in all the expressions, the numerator is same, that is Z1, Z2, Z2, Z3, then Z3, Z1. So it is common. So let us see how to write the denominator. For example, if you take ZA, you take ZA. So numerator you write Z1, Z2 plus Z1, Z3 plus Z2, Z3. So exactly you see what is the impedance opposite to this in the star connected network. It is Z1. So you have to write Z1. Similarly for ZB, numerator is same, and ZB is here the opposite impedance in the star connected network is Z2. So you write Z2. Similarly ZC, opposite impedance is Z3, so you write it. So this is how you have to write it. Now let us consider this problem. Find the total impedance ZT of the network shown in figure below. So this is the network. So if you see this network as it is not possible to reduce the network and find out the equivalent impedance. So here there are two delta networks and two star networks. So this is one delta, and this can be considered as one delta, and this is one star, and this is also another star. So you can select either star or a delta network and convert that into another, so that further reduction is possible. So in this case, we'll convert this delta connected network into star. So first thing what you have to do is, so you name here 1, 2 and 3. So 1, 2, 3. So this impedance between 1 and 2, you name it as ZP, and 1 and 3 you name it as ZC, and this one you name it as ZA. So first you name it like this, and you know that how you have to connect the star connected impedance. So opposite to ZA you have to place Z1. So Z1 will be connecting to node 1, and ZB is here, therefore Z2 should be connected to this node 3, and similarly ZC is here, therefore Z3 should be connected to this opposite node, that is node 2. So now ZA is minus J4 ohms, capacitance only ohms is given, so you have to write it as minus J4 ohms, and ZA is this plus minus J4 ohms, and ZC is 3 plus J4, you have to write plus J4 ohms. So now you substitute in the formula Z1 equal to ZB into ZC by ZA plus ZB plus ZC. So if you substitute, right, you will get the value of Z1. Similarly, this is the value of Z1, that is 3.84 plus J 1.11 ohms. Similarly, find Z2 using this formula, ZA ZC divided by ZA plus ZB plus ZC. So you'll get 3.84 plus J 1.11 ohms. Then similarly find Z3, you'll get this value as minus 1.92 minus J 2.56. So now the values are written here. So we have found out Z1, Z2, Z3, and the Z4 is 2 ohms and Z5 is 3 ohms. So you see the original circuit, this is considered as Z4 and this 4 is Z5. So now you draw a circuit history around here. The delta connected network, it is replaced by the star connected network, and they are connected to the proper terminals. So now you'll find that in this, these two impedances are in series and these two are in series. So you can make this as one. I'm calling it as ZT1, that is Z1 plus Z4. You find out this 5.94 at an angle 10.76 degrees. Similarly, you combine this and call it as ZT2. So ZT2 is Z2 plus Z4. So Z2 plus Z4, this comes to be around 6.93 at an angle 9.22 degrees. Now this is ZT1 and this is ZT2. They are in parallel. Find the equivalent impedance. ZT1 into ZT2 divided by ZT1 plus ZT2. Substitute the values, you'll get 3.198 at an angle 10.05 ohms. So this in rectangular form, it is 3.15 plus J into 0.56 ohms. Now this entire part you have reduced to a single resistance. This resistance comes in series with Z3. So Z3 and ZT3, they are in series. So add them. So you'll get this value is 1.23 minus J is 2.0. This also will be equal to 2.35 at an angle minus 58.41 degrees. So this is how you should find out the total impedance of the network. Coming to source transformation. So we can convert a voltage source into a current source, as we have seen in DC circuits. So the source transformation in frequency domain involves transforming a voltage source in series with an impedance, that is here voltage source in series with an impedance, to a current source in parallel with impedance, or vice versa. So if this can be converted like this, or this can be converted to like this. Suppose you are going to convert this to this, then the current Is will be equal to Vs divided by Zs, and Zs you have to draw in parallel. So current source in parallel with impedance. This is how you have to convert voltage source to current source. Similarly, if you have a current source in parallel with the impedance, this can be converted into voltage source in series with impedance. That is, if you want voltage source to multiply Es with Zs, so you'll get this voltage, and Zs you draw in series. Now consider this example. Calculate Vx in the circuit using the method of source transformation. So here you are asked to calculate this Vx. You have to use source transformation and do this. So if you are going to apply source transformation, what you have to do is you have to reduce this circuit to this form. Then finally you can apply voltage division rule and find out Vx. So now what we will do is, first we will take this voltage source and in series with this resistance. This is the voltage source. So this voltage source in series with resistance, you convert this into current source in parallel with the resistance. So this resistance you now draw it in parallel. The current will be 20 and angle minus 90 divided by 5. This comes to be minus J4. So minus J4 ampere we write here. So now you have done this. Now what you do is, these two impedances are in parallel. So you can reduce this to a single impedance. That is, I am calling that impedance as Z1. That is 5 into this branch is 3 plus J4 divided by 5 plus 3 plus J4. That is 8 plus J4. So this comes to be around 2.5 plus J 1.25 ohms. So this is the equivalent impedance of these two parallel impedances. So now what I will do is, so I have a current source in parallel with single resistance equivalent to this. So now the current source in parallel with that impedance is Z1. Now you can convert that into a voltage source in series with the resistance. So in that case, the voltage source will be Is into that impedance is Z1. So this comes to be 5 minus J10. So you write it here. Now, and the impedance will be here, that is 2.5 plus J 1.25. So that you have to write here. So now this circuit, right, if you see, it is a very simple circuit, series circuit. You have a voltage source and series with the reactance and resistances. So now you apply voltage division rule and find out the voltage across this resistance. So the voltage formula will be this voltage, that is 5 minus J10 multiplied by this resistance, that is 10 ohms, divided by sum of all the resistances and reactances in the circuit, that is 2.5 plus J 1.25 plus 4 minus J 13 plus 10. So this gives you value as 5.519 at an angle minus 28 degree volts. So this is how you should apply this source transformation and reduce the circuit to this simple circuit and find out the voltage. Coming to the Thevenin and Norton's theorem. So as we have seen how to obtain the Thevenin and Norton circuit for DC circuit, similarly we can also obtain the Thevenin and Norton's equivalent circuits for AC circuits as well. So here, if we have a linear circuit and between the two terminals A and B, this linear circuit can be converted into a voltage source in series with the impedance. So this entire network between the terminals is reduced to a simple network consisting of voltage source and impedance. This voltage is called as Thevenin voltage. This impedance is called as Thevenin impedance. So Norton circuit, right? This network can be reduced to a current source in parallel with Norton impedance. So Norton impedance and Thevenin impedance are same. You have to find out in the same way. And current is Norton current. So here you can relate this VTH and IN like this. So VTH will be equal to IN into Zn, and you try to remember Zn will be equal to ZTH. So now consider this problem. Obtain the Thevenin equivalent circuit at terminals A, B in the circuit. So you are asked to find the Thevenin equivalent circuit between the two terminals. So that the circuit between the two terminals should be converted into a single voltage source in series with the impedance. So to find ZTH, what you have to do is set the voltage source to 0. So you have to set this to 0. You have to create a short circuit. So here this node is marked as D, this node is marked as F. So now you redraw this circuit. So now this 8 ohms comes in parallel with minus J6, and similarly this 4 ohms comes in parallel with J12. So you draw the network like this. So now these two are in parallel, these two are in parallel. So now find, you call this as Z1 and this as Z2. Z1 is 8 parallel with minus J6. So this gives you 2.88 minus J 3.84. Similarly, Z2 4 in past J12. That this gives us 3.6 plus J 1.2 ohms. So now we know this impedance, that is Z1, and this impedance we have called as Z2. So now the total impedance between the terminals A and B will be equal to sum of the two impedances. That is ZTH will be equal to Z1 plus Z2, which will be equal to 6.48 minus J 2.64 ohms. Now to find VTH, Thevenin voltage, you solve this circuit and find out the voltage between the two terminals. Here you find I1 and I2. So you know that this voltage is connected across this branch. So if you divide this voltage to 120 at an angle 75 degree divided by the impedance of this branch, you will get this current. That is 8 minus J6 is the impedance of this branch. So you will get current I1. Similarly, I2, you divide this voltage by the total impedance of this network, that is 4 plus J2. So you will get current. Now take this mesh and write the KVL equation. So you can write like this. So the polarity is like this. So this end is plus, this end is minus, and here the current entering end is plus and this end is minus, and here current entering end is plus, this is minus. So therefore we can write like this: plus VTH minus I2 into 4 plus I1 into minus J6 equal to 0. Just you write the KVL equation for this mesh. So this is the equation. So from this you find VTH will be equal to 4I2 plus J6I1. Substitute all the values, you will get this value as 37.95 at an angle 220.31 volts in polar form. In rectangular form it is minus 28.936 minus J2 24.55. So this is the equivalent Thevenin's network. Suppose you are asked to find the current in the load impedance. If the load impedance is given some value and you have to connect that load impedance across the terminals and you have to solve the circuit. So the current in that circuit will be VTH divided by ZTH plus ZL. You can find out the current. So as to power consumed by the load, suppose the load is having some resistance. Using this formula, that is square of the magnitude of current multiplied by the resistance gives us power. Now another example we will see. Find the Thevenin equivalent circuit from terminals AB. It has to find out. But here we have a dependent source, that is 0.5 I0. So now let us see how to get the Thevenin equivalent circuit. To find VTH, so you apply KCL at node 1. So node 1 is here. So you make this as node 1, this is node 2, you mark all the currents. So this is already current is given, source current, so you have the same direction. So I0 is also indicated in the circuit. For this you mark the current as 0.5 I0. So why it is marked as 0.5 I0? Because this current source is here. So the current, whatever the current is flowing here only will be flowing in this branch. So the current in this branch also will be 0.5 I0. So now if you apply, so the incoming current will be equal to outgoing currents. So the 15 will be equal to I0 plus 0.5 I0. So from this find out I0. So you will get 10 ampere. Then apply KVL to the middle loop. You apply KVL for this. That is minus I0 into 2 minus J4. Then plus 0.5 I0 into 4 plus J3. And you keep this voltage as VTH. So plus VTH equal to 0. So you are writing this equation. So first of all, you have assigned the current. You are traveling like this in the clockwise direction. So the current direction is marked. So this end is plus, this end is minus. And whereas here, this end is plus and this end is minus. If you are going to conserve this current. Since you are going to use this current, the polarity will be this end will be plus and this end will be minus. So you can write this equation, find out VTH. VTH will be equal to 55 at an angle minus 90 degree. Then to find out ZTH, what you have to do is a 3 ampere current source is connected here. So even you can connect an 1 ampere current source. Here it is, here in this circuit we have connected 3 ampere source. That current is called as IS. Now what you do is, so solve this circuit, find out Vs and Is. Is already we know. So if you're going to divide Vs by Is, you will get the equivalent impedance of the network across the terminals. So now at node 3 is the incoming current and these two are outgoing currents, plus 0.5 I0 plus I0, right? So the current in this branch already in the circuit, it is marked as I0. So this is the equation for this node. So from this you find I0. So now applying KVL to the outer loop, you apply KVL to this outer loop. So in this case, this will be equal to Vs will be equal to the drop across this, that is I0 into 4 plus J3. Then drop across this will be I0 into 2 minus J4. So this is what it is written here. I0 is, if you take common, you have to add all the resistance and reactances in this part, right? So you are going to travel like this. So this comes to be around 2 into 6 minus J. So the Thevenin impedance is Vs by Is. So Vs you divide by the Is, you will get this value. So you can assume even 1 ampere current. So now with this Thevenin impedance and Thevenin voltage, you can draw the equivalent circuit. Next, obtained I0 for using Norton's theorem. So let us find out the Norton equivalent circuit. To find ZTH, so now what you have to do is you have to remove the source and create your open circuit here. To find out ZTH, first we have to remove the voltage source and create a short circuit. So remove the source, create a short circuit. And if you have current source, you have to create your open circuit, remove it. So in order to find ZTH, which will be equal to Zn. So now you remove this voltage source and create a short circuit, and remove this current source, and you remove this impedance across terminals AB. So the circuit will be looking like this. So here these two branches comes in series and this comes in parallel with the short circuit. So the equivalent resistance in this case it will be 0. So 0 in parallel with any impedance will give us the equivalent value as 0. So 0 comes in series with 5 ohms. So you get the impedance as 5 ohms. To find out the Norton current, you take this circuit and you create a short circuit across the terminals AB, create a short circuit and find the current in this branch. So now what we'll do is, if you look at this circuit, we will use mesh analysis to find out the current in this mesh, that is I3. If you know I3, this will be equal to IN. So here, since this current source is common between mesh 2 and mesh 3, we have to form a super mesh involving these two meshes. So this mesh super mesh is shown here. Now we have to write the equations. For mesh 1, the equation will be, you travel like this, current directions are assumed here in the clockwise direction. So this source voltage will be minus 40 plus the coefficient of I1s. You add all the resistances and reactances in this mesh, that is 10 plus 8 is 18 and minus J2 plus J4 is plus J2, that is 18 plus J2 into I1. Coming to this I2, you have first, while considering first mesh, you have to find out which elements are common between first mesh and second mesh, that is 8 minus J2 is common and the current direction opposite. So you have to write minus of 8 minus J2 into I2. Coming to the, while writing I3, so you have to consider which resistance and reactance are common between first mesh and third mesh, that is 10 plus J4. So you see the current direction, so they're opposite. So you have to write minus 10 plus J4 into I3 is equal to 0. So the algebraic sum of the voltage drops across the elements equal to 0. So for super mesh, you have to consider these two meshes and write the equation. So that is, the equation is, for this mesh 2, so you have to add all the resistances and reactance, that is 8 plus 5 is 30 minus J2 into I2 you have to write for this. And for I3, the total impedance and reactance in this mesh is 10 plus J4. So 10 plus J4 into I3. Then this super mesh is in common with this mesh, first mesh. So therefore, in the first mesh, we have the total resistance and reactance as 8 plus 10, 80 minus J2 plus J4. So 18 plus J2. So, and you check the current directions. They are opposites. So therefore, you write minus 18 plus J2 into I1 equal to 0. So you have two equations. Now we can write this current as I3 minus I2 equal to 3 ampere. So I3 is direction is same as 3 ampere. So I'm writing I3 minus I2. This I2 is opposite to that of this current direction. So I3 minus I2 equal to 3 ampere, or I3 equal to I2 plus 3. So now you adding equations 1 and 2. If you add these two equations, you will get, you can find I2 as J8. And from, so now this I2 we substitute in equation 3. So we get 3 plus J8. So now you got I3. So this is the value. So now the Norton current will be equal to IN. That will be equal to I3. So now we have found out the mesh current I3. So that will be IN. So that will be equal to 3 plus J8 ampere. So after finding Norton current, already we have found out the Norton impedance, which also will be equal to Thevenin impedance. So you have to draw the circuit. 3 plus J8 is the Norton current and 5 is the Norton impedance. And across this, you connect the load impedance, that is 20 plus J5. You are asked to find current in this branch. Now this is a simple circuit. You can find current in this branch. So to find current in this branch, use current division rule. So total current is 3 plus J 8 ampere. So this multiply by opposite branch impedance is 5 divided by sum of the impedance of two branches, that is 5 plus 20 plus J50. So this comes to be around 1.465 at an angle 38.48 degree ampere. Then maximum power transfer theorem in AC circuits. So here the load is usually represented by ZL. So it can be a motor or antenna or TV, it can be anything. So here circuit, right? That the circuit between the two terminals, between the load terminals, can be reduced into a Thevenin network consisting of voltage source and Thevenin impedance. And then you connect this load impedance across the terminals and let I is the current in the circuit. So now ZTH will be equal to RTH plus JTH. I am writing this impedance as, that is real part as RTH, resistance part, and the imaginary part as XTH, that is JXTH. Similarly, load impedance I am writing it as RL plus JXL. So now you can find out the current in this. I will be VTH divided by total impedance of the circuit ZTH plus ZL. So now you can write the equation for power. Power is the magnitude square multiplied by the resistance RL. So this will be VTH square into RL divided by RTH plus RL whole square plus XTH plus XL whole square. So now to find out the impedance for which maximum power will be transferred from this circuit to this load impedance, you differentiate this power and equate it to 0. So now we'll do first case as you differentiate power with respect to XL equated to 0. You will get XL equal to minus XTH. Similarly, you differentiate power with respect to RL equal to 0. So in this case, you will get XL equal to minus XTH. So now the RL we will get it as under the root of RTH square plus XTH plus XL. Maximum power to be transferred from this circuit, source circuit, to this load impedance. The load impedance should be equal to RTH minus JTH. That is, it should be complex conjugate of the Thevenin impedance. So RL should be equal to RTH and XL should be equal to minus XTH. So this we call it as complex conjugate of the Thevenin impedance. So for the maximum average power to be transferred from the source circuit to the load impedance, ZL load impedance must be equal to complex conjugate of the Thevenin impedance. So RL should be made equal to RTH and XL should be made equal to minus XTH. This means that for maximum power transfer to a purely resistive load, the load impedance or resistance is equal to the magnitude of Thevenin impedance. So determine the load impedance that maximizes the power drawn from the circuit or figure. What is the maximum average power? So this is a circuit. So voltage source, resistance, capacitive reactance, inductive reactance, and etc. So for this circuit to supply maximum power to this, to find out the load impedance and the power. To find out the load impedance for which maximum power will be transferred from this circuit to this. So you draw the equivalent circuit to find out the Thevenin impedance. So you remove the source, create a short circuit. Now these two branch impedance will be in parallel. This comes in series with J5 ohms. So now you find out ZTH. Similar to find VTH, what you have to do is you take this circuit, you remove this ZL, find out the open circuit voltage across these two terminals. So now this circuit looks like a simple circuit. since it is this part is open circuit, so current in this branch will be 0. So therefore only the current will be flowing in the closed path. So you find out the current, and to get the voltage across this branch you multiply current with this branch impedance. So that will be the voltage VTH also. So now ZTH will be 8 in parallel with 8 plus 8 minus J6. This comes in series with J5. So this comes to be around 2.933 plus J 4.467. Now find VTH. So you take the circuit, you assign current in this path as I1. So this I can write it as I1 into 8 minus J6. The current I1 is voltage divided by the total impedance, that is 8 plus 4 plus minus J6. So therefore I1 is 10 plus J0 divided by 4 plus 8 minus J6 multiply by this 8 minus J6. So this comes to be around 7.33 minus J 1.33, which will be equal to 7.45 at an angle 40.3 volts. So this is how you should find out VTH and ZTH to find out maximum power. So from this circuit you have to find out the maximum power drawn by the load impedance. So for this you have to find out the current. You make Z equal to complex conjugate of this Thevenin impedance. So ZTH star, this is nothing but complex conjugate of this impedance. So its value is 2.933 minus J 4.467. So the current in this circuit will be equal to VTH divided by the total impedance, that is ZTH plus ZTH star. So now to find current, you divide this voltage by ZTH plus the complex conjugate of this impedance. So this comes to be around 1.27 at an angle minus 10.3 degree ampere. To find out the maximum power drawn by the load impedance, we all know that the load impedance now it has got the resistance as 2.933 and reactance parts as minus J 4.467. So only the resistance will be consuming power. Therefore, you find maximum power by using this equation, I square into R. The magnitude of current is 1.25 square into the resistance value is, that is real component of load impedance is 2.933. This comes to be around 4.73 watts. That's all about this presentation. I hope you have understood the concepts and problems discussed in this presentation. Thank you.